Welcome to lecture 22. The topic is p-adic expansions for p-adic integers. So this is lecture 22. The topic that we want to consider, it's p-adic expansions for the p-adic integers, which we call ZP. And just to recall and give some motivation, when you have this abstract construction of real numbers from Q, we have this abstract construction of the real numbers from Q. Again, and how does it go? Again, we just consider quotients of Cauchy sequences, and again, now if you want to consider real numbers, the Cauchy sequence is with respect to the Archimedean absolute value an, where these an belong to rational numbers, and then you mod out by all the null sequences. Okay, so this is somehow an abstract construction to show that R exists, but no one really thinks of an element, a real number, as an equivalence class of Cauchy sequences. So it is very cumbersome to think of elements of R as equivalence classes of Cauchy sequences. And when I talk about a real number, what most people think about is its decimal expansion, for example. Instead, one usually thinks of elements of R involving some decimal expansion. Usually we work with the base 10 expansion. So for example, you have square root 2. The decimal expansion is 1.414213, so on and so forth. If you have pi, its decimal expansion is 3.14159, and so on and so forth. Instead of just thinking of an arbitrary Cauchy sequence to represent elements of R, for square root 2, for example, you think of 1, 1.4, 1.41, 1.414, 1.4142, and so on. And similarly for pi, the Cauchy sequence that you want to consider is 3, 3.1, 3.14, 3.141, and so on and so forth. So somehow we have this convenient sequence that we all think of, and correspondingly we have this decimal expansion for an arbitrary element in base 10. So you write this as an 10 raised to n, where you could start from minus infinity, but then you cap off somewhere at m. And so these ans, they belong to 0, 1, 2, all the way up till 9. Okay, and so the goal is to consider analogs of decimal expansions for p-adic integers. So we are searching for an analogous expansion for ZP, and this expansion is what we call this p-adic expansion. Again, the whole goal is we don't want to think of elements of ZP as equivalence classes of Cauchy sequences, but rather we want to work with some specific p-adic expansion. And again, just to recall the various elements, so we have the rational numbers sitting inside QP, and we thought of QP as this quotient C over n, where the C was Cauchy sequences with respect to the p-adic absolute value, that the ans are rational numbers, and then L and N was all the null sequences, and QP is the completion. So we had this whole process because Q was not complete with respect to the p-adic absolute value, and when we complete it we get QP. So QP is the completion of Q with respect to the p-adic absolute value. And sometimes this is also called the p-adic completion. And so in other words, Q is dense inside QP. And so for any element alpha in QP, we can find a sequence, say a Cauchy sequence AN with AN and Q, such that if you take the p-adic limit of these ANs, you get alpha. And similarly, well, we have Z inside ZP, and the way we defined that ZP was this was the evaluation ring of QP. And one of the results that we proved in the last lecture was that ZP, we also call this, we saw that this was equal to a ring Z1, which was this quotient CZ by NZ, where again CZ was the ring of Cauchy sequences AN, again Cauchy with respect to the p-adic absolute value, where now the ANs just belong to Z, and NZ was the ideal of null sequences inside CZ. And so you see that this somehow mirrors the construction of QP by completing Q with respect to the p-adic absolute value. So similarly, what we have is that ZP is the completion of Z with respect to the p-adic absolute value. Okay, and if you recall what we also showed, we had this other ring Z localized at P, the DVR. This was also mapped to ZP, and we had the second description of ZP as Z2, which was C of Z localized at P modded out by the null sequences, where again CZP was these Cauchy sequences, again with respect to the p-adic absolute value, where each of these ANs now belongs to the DVR Z localized at P, and NZ localized at P was the ideal of null sequences. And again, this description tells you that ZP can also be viewed as the p-adic completion of this DVR with respect to the p-adic absolute value. Okay, but just for simplicity, we'll just work with this fact that ZP is the completion of Z with respect to the p-adic absolute value. Okay, and again, sometimes I'll call this p-adic completion just to emphasize that we're completing with respect to the p-adic absolute value. So we have that ZP is the completion of Z with respect to the p-adic absolute value, and again what that means is, in particular, for any alpha in ZP, there exists a Cauchy sequence say AN, where these ANs are integers such that the limit as n goes to infinity of the ANs equals alpha. Okay, and so the goal to find a p-adic expansion for alpha, the goal is really to find an optimal Cauchy sequence an, there are, all these ans are in Z. So that they approximate alpha. Okay, so we want to find good approximations in Z for alpha when alpha is a p-adic integer. And so I just want to recall some facts from algebra, or maybe you can call it elementary number theory. If you take an element, let's say in Z mod p to the n Z, an elementary fact is that it has a unique representative alpha n in Z with the property that this alpha n is between 0 and p to the n. It could equal 0, but I'm not allowing the possibility that it equals p to the n. Okay, and furthermore, under the natural surjection, from Z mod p to the n to Z mod p to the n minus 1, suppose you have that alpha n, say maps to alpha to the n minus 1. Now what does it mean? Now my alpha n is chosen to be between 0 and p to the n. My alpha n minus 1 is chosen between 0 and p to the n minus 1. And if alpha n maps to alpha to the n minus 1, they belong to the same congruence class in Z mod p to the n minus 1. So that just means that alpha n is congruent to alpha to the n, alpha n is congruent to alpha n minus 1 modulo p raised to n minus 1. Okay, so in particular, if you look at this ratio, alpha n minus 1 over p raised to n minus 1, that's an integer, and I'll call it dn minus 1. Okay, an observation, a really elementary observation, is that this integer dn minus 1 should be between 0 and p minus 1. So it should belong to this finite set 0, 1, 2 all the way up to p minus 1. And why is that? If you just rewrite this expression, dn minus 1 is alpha n minus 1 over p to the n minus 1. It just means that alpha n is alpha n minus 1 plus dn minus 1 times p raised to n minus 1. If this digit, let's say dn minus 1, was less than 0, then you see that alpha n has to be less than 0, as alpha n minus 1 is strictly less than p to the n minus 1. But this is not possible, since by our choice alpha n is larger than or equal to 0. And again, if dn minus 1 is larger than p minus 1, then you see that alpha n has to be larger than or equal to p to the n. And again, it's not possible, because alpha n is chosen to be strictly less than p to the n. Since alpha n is strictly less than p to the n, we cannot have this possibility that dn minus 1 is larger than p minus 1. So dn minus 1 cannot be less than 0, it can't be larger than p minus 1, it's an integer. So the only possibility is that it's an integer that's in this finite set 0, 1, 2, 3 up to p minus 1. Okay. So what's our game? So given an alpha in Zp, first of all we choose an an in Z, so that the distance between alpha and an, by which I mean the p-adic absolute value of the difference alpha minus an, is less than 1 over p to the n. Okay, and again this is possible So given an alpha and zp, I can choose a sequence an in z such that alpha minus an in p-adic absolute value is less than 1 over p to the n. This is possible since z is dense in zp, as zp is the p-adic completion of z. Okay, and so by construction of these ANs, the sequence ANs, this is a Cauchy sequence. So you see that the limit as n goes to infinity of 1 over p to the n equals 0. So by construction, the sequence an is a Cauchy sequence with the property that the limit as n goes to infinity of an equals alpha. Okay. Now I want to choose my ANs, my integers, a bit more optimally. So I'll use a few of the observations that I made earlier. Now for each AN, I choose an alpha n in Z such that this alpha n is between 0 and p to the n, with the property that alpha n is congruent to an mod p to the n. Okay, and what that means is that this just means that in Z mod p to the n Z, alpha n and an, they represent the same elements. And again, what this means is that when you take alpha n and a n, you take the difference and compute the p-adic absolute value, you see that they correspond to the same element in Z mod p to the n. So the difference is divisible by p to the n, which means its p-adic valuation is at least n. So if you take the p-adic absolute value, this is less than equal to 1 over p to the n. Okay, and so thus, if you look at the difference of alpha and alpha n in p-adic absolute value, you play this trick of adding and subtracting an, and use the ultrametric inequality. You get that this is less than equal to the maximum of the p-adic absolute value of the difference of alpha and an, and the p-adic absolute value of the difference of an and alpha n. Now on the one hand, the p-adic absolute value of the difference of an and alpha n, that's less than equal to 1 over p to the n. But by construction of these ANs, the p-adic absolute value of the difference between alpha and an, that's also less than 1 over p to the n. So this first quantity is also less than equal to 1 over p to the n. So I'm considering the maximum of two quantities, both of which are less than equal to 1 over p to the n. So this means that the p-adic absolute value of the difference of alpha and alpha n, this is also less than 1 over p to the n. So again, the sequence of alpha n's, these are Cauchy, since 1 over p to the n just goes to 0, and the sequence alpha n is compatible in the sense that I've chosen my alpha n so that they're between 0 and p to the n. If I take alpha n minus 1, that's between 0 and p to the n minus 1. But what I also have is that alpha n and alpha n minus 1, they're congruent mod p to the n minus 1. Now, the first two conditions, they're obvious by construction. So the first two conditions are obvious by construction, and so the question really is, why does the third condition hold? And again, to see that the third condition holds, you again look at the p-adic absolute value of the difference of alpha n and alpha n minus 1, and play the same trick of adding and subtracting a number, in this case alpha, And the trick again is to use this ultrametric inequality. So you have the p-adic absolute value of the difference of alpha n and alpha n minus 1. But on the one hand, if you look at the p-adic absolute value of the difference of alpha n minus 1, this is nothing but it's less than 1 over p to the n minus 1. And if you look at the first quantity, this is nothing but the difference of alpha n in p-adic absolute value, and we know that this is less than equal to 1 over p to the n. And so the maximum of these two quantities is 1 over p to the n minus 1. So we have that alpha n minus 1 in p-adic absolute value is less than 1 over p to the n minus 1. And again, what this means is that since alpha n and alpha n minus 1 are integers, this just means that the difference is divisible by p raised to n minus 1, or in other words, alpha n and alpha n minus 1 are congruent mod p raised to n minus 1. Okay, so we have this compatible sequence of alpha n's, and so let's just unwind from the start. So we have this digit d0, which is what we call alpha 1, where d0 belongs to 0, 1, 2 up to p minus 1. Now if you look at alpha 2, again by construction this is alpha 1 plus d1 p raised to 1, with the property that d1 is also between 0 and p minus 1. And now if you plug in the formula for alpha 1, you get alpha 2 is d0 plus d1 p raised to 1. Okay. So we started with d0 and added an extra term d1 p1. Now play the same game with alpha 3. Again, by definition, alpha 3 is alpha 2 plus d2 p2. Again, this digit d2 lies between 0 and p minus 1. And now again, if you unwind this formula for alpha 2, you get d0 plus d1 p raised to 1 plus d2 p squared. Okay, so you see that at each successive step, you add a power of p that's larger than the previous step, and then you multiply that with the digit that's between 0 and p minus 1. So in particular, at the nth step, you have d0 plus d1 p raised to 1 plus d square p square, and so on and so forth, dn minus 1 p raised to n minus 1. Okay, and so this is, so the expression summation n equals 0 to infinity di p raised to I, where each of these digits are between 0 and p minus 1. This is said to be the p-adic expansion of alpha. Okay, and it's not hard to see that given such an expression, given such a sequence where you have alpha 0 equals d0, alpha 1 is d0, alpha 2 is d0 plus d1 p1, and so on and so forth. Alpha n is d0, d1 p1, so on, dn minus 1 p raised to n minus 1. Let's say an alpha m is d0 plus d1 p1, all the way up to dm minus 1 p raised to m minus 1. So suppose you're given such a compatible sequence where each of the di's, they're between 0 and p minus 1. So it's not hard to see that such a sequence is Cauchy, since if you take an m that's larger than n and you compute the difference of alpha m and alpha n, you see that all the terms involving powers p raised to 0, p raised to 1, all the way up to p raised to n minus 1, they cancel off. And so you get that this difference starts with this power p to the n plus higher order terms involving p raised to, say, I. And so in particular, if you take the p-adic absolute value of the difference, this is less than or equal to 1 over p to the n. Okay, and so this shows that such sequence, and so the above inequality is true whenever this m is larger than or equal to n, and so this shows that the sequence above is Cauchy. With respect to the p-adic absolute value. Okay. And so the last observation that we want to make is that such an expression, such a p-adic expansion is unique. So given an alpha, you have a unique p-adic expansion. And so the last observation that we want to make is that the p-adic expansion for each alpha and zp is uniquely determined by the digits di. Again, why is that the case? Suppose you have alpha and you have, let's say, two distinct p-adic expansions, say summation di p raised to I and summation ei p raised to I are two distinct p-adic expansions of alpha, and so the di's and the ei's, they belong to the set 0, 1 up to p minus 1. Okay, so if you take the difference, you get that 0 equals summation I equals 0 to infinity of di minus ei times p raised to I. And now you choose, you have these digits, and we are assuming that they correspond to the p-adic expansions of the same number, but somehow the p-adic expansions themselves are distinct. So these digits di and ei, they must be distinct for some indices. So you take the minimum index I such that di is not equal to ei. Okay, so such a minimum exists. So such a minimum exists since we've assumed that the p-adic expansions are distinct. And so let V be this minimum. And now what we have is that D, so this expansion, it sort of starts with dV minus EV times P raised to V plus higher order terms involving, say, some P to the I, where all these exponents I now are larger than, strictly larger than V. But since now dV is in this finite set 0 up to p minus 1, and EV is also in this set 0 up to p minus 1. Now it's not hard, and what we also have is that dV is not equal to EV, so it's not hard to show that this difference dV minus EV is not divisible by p. Okay, so it's an easy exercise, and so in particular, What that means is that if you look at this expression, so the right hand side, so what this means in particular is that if you look at, say, the right hand side and evaluate the p-adic absolute value, this is exactly 1 over p to the v, with this v being a natural number. But if you look at the left hand side, that's 0, and the p-adic absolute value of 0 is nothing but 0. This is a contradiction. And so the only possibility is that the p-adic expansions are the same. Okay, so in summary, what we've shown is that every element in ZP has a unique p-adic expansion summation di p raised to I, where these digits di belong to 0 up to p minus 1. Okay, and an interesting corollary of this observation is that the residue field of ZP equals Z mod PZ, which some people also call FP. Okay, and so a quick proof of this. So we have that Z sits inside ZP, and if you want to think of ZP as equivalence classes of Cauchy sequences, you know, if you have an integer x, you send it to the constant Cauchy sequence, and under this inclusion, PZ gets mapped to PZP, which, let me remind you, by lemma 48, PZP is the maximal ideal of the evaluation ring ZP. So this inclusion, under this inclusion, you have Z going into ZP, and we have PZ sits inside PZP. So we have an induced injection Z mod PZ sits inside ZP mod PZP. Now again, since PZP is a maximal ideal of ZP, this is a field. And since PZ is a maximal ideal of Z, this is also a field, which is often called FP. And so the goal, so what we want to show is that this injection is surjective. So you take an arbitrary element alpha in ZP and write its p-adic expansion. So write this as d0 plus d1p plus d2p square, and so on and so forth. But I'm only interested in alpha modulo pzp. So I only care about things up to this, up to elements in pzp. So you can write alpha as d naught, and now you collect the powers of p. So you have p times d1 plus d2p plus so on and so forth. Okay, so this new expression, let's call that beta. So in short, we have that alpha is d naught plus p times beta. Okay, and so thus what we have is that inside zp mod pzp, the class of alpha equals the class of d naught. Okay, so here these digits di's, they belong to 0, 1 up to p minus 1. And in particular, so the class of alpha is given by the class of this integer d naught. So this shows that the injection is in fact surjective, since if I take an arbitrary element alpha and take its class there, I look at its p-adic expansion, look at the first digit, and what I've just observed is that d naught maps to alpha. So this shows surjectivity, and so this completes the proof of the corollary. Okay, so that completes the discussion on p-adic expansions of ZP. Thank you.